Hi students, welcome to the lecture on mass spectrometry and the Diels-Alder reaction. All right, we're going to go through these PowerPoint slides, and as I talked about before, we are going to be talking about mass spectrometry and then talk a little bit about the Diels-Alder reaction, which should correspond to your lecture this week as well. Okay, so in mass spectrometry, we're primarily using this technique to determine the molar mass of a compound and or the formula for a compound. And the way it works in a mass spectrometer, the compound is introduced into the instrument. Notice where it says on the picture here, sample molecules enter here, right? They get heated up and vaporized, so they go into the gas phase. And then once in the gas phase, they can go through an electron slit, which basically is a high energy beam of electrons. And if the electron hits the molecule in the gas phase, then an electron can get ejected to form an ion. And then the ion goes through an accelerating process where it accelerates, and as it comes into a potential turn, so you can see the north and south of the magnetic field. So it's passed through a magnetic field, and only compounds that are charged are deflected by the magnetic field. So they would make the turn and then eventually reach the detector and be detected and show up on the spectrum. So the most common method of ionizing molecules, and really the original method, is the electron impact, which was what you saw in the picture on the last slide. But there are other methods of creating ions, including ones we'll talk about later. So instead of EI for electron impact, you might hear about ESI, which stands for electron spray ionization, and also APCI, which stands for atmospheric pressure chemical ionization. So there are multiple methods or ways of generating ions on compounds that can then pass through the magnetic field, be deflected, and reach the detector. Some of them are more damaging, basically, than others. So meaning it's called a harsh method of forming an ion, where then that ion also gets a lot of energy and then can fragment. And so the EI is the most high energy form of forming the ions, and therefore it is subjected to the most fragmentation that we'll talk about. So ESI and APCI are considered more gentle methods of ionizing. The molecules don't have as much energy after being ionized by those methods, and therefore they tend to stay more intact, which is actually an advantage. We'll be able to see what's called the molecular ion more commonly with that, and so usually that's what we want to see, but we're going to talk about that more. But in EI, the sample again is bombarded with that beam of high energy electrons, and the electron, if it knocks into a molecule, can actually eject another electron from the molecule right out of that molecule. So essentially an electron would come and attack the molecule you see here, right? And it would actually eject one of the electrons potentially from this molecule. When that happens, you get the electron, and then you get what's called the radical cation. It's called that because, of course, once it's lost an electron, it has an unpaired electron. That's called a radical. And one of the carbons has less than an octet, so it's a cation as well. So again, that radical cation from the original molecule is going to be called the parent ion or the molecular ion. Right, so the structure you see in brackets, the radical cation, because there hasn't been any fragmentation yet, we were going to call this the parent ion or the molecular ion. And again, because it's charged, it would be deflected by the magnetic field and it would reach the detector. And that's actually what we want to see. We want to see the radical cation of the parent molecule or the original molecule, so known as the molecular ion. We want to see that reach a detector, because that's how we'll know the mass of the compound. because the mass of the electron ejected is negligible compared to the mass of the original molecule. Because remember that protons and neutrons are much more heavy than electrons. So losing one electron is not losing much mass at all. And essentially the mass of the molecular ion is equivalent then to the mass of the original molecule. And that way we know what the mass of the molecule is, and that's really what we're going for with this type of analysis. Okay, sometimes the parent ion or the molecular ion is so high energy it's not very stable, in which case it can start to fragment or break into pieces. And one such thing that can happen, right, is to break the carbon-carbon bond that only has one electron in it now. It's not a very stable bond, so you could undergo a homolytic cleavage. One side gets the electron, one side doesn't, and you end up with a radical species and a carbocation species. So this is something ideally we don't want to happen actually, because then we see a bunch of fragment peaks which are a little bit harder to analyze than the molecular ion. And interestingly, only the carbocation would get deflected by the magnetic field. So the radical doesn't actually make it to the detector, only the carbocation does. On the x-axis of a mass spectrum, it says it's called m/z, which stands for mass to charge. So basically it's the mass divided by the charge of an ion. And remember, only ions reach the detector, so there's always a charge, right, of +1 is very common. So since it's always pretty much +1, z is equal to 1. So on the x-axis, it really just corresponds to the mass. Okay, so this is an example of a mass spectrum of methane, right? We can see that there are a number of peaks here. There's not just one peak, but a number of peaks. So let's analyze that. The first thing we want to take note of is the tallest peak. You can see that the tallest peak here is at a mass to charge of 16. That is actually the molecular ion or the parent ion for methane. We can do a quick calculation to double check that. What we would do is basically take 12 for the mass of carbon and add 1 each for each hydrogen. So 12 plus 4 is 16, so we would expect the molecular ion for methane, right, to be 16. Remember that the peak here at 16 represents the molecule after it's lost an electron. But again, that electron mass is negligible, so it's still 16. We do see some other peaks, right? The next highest one is 15, then you see 14, 13, and 12. That's actually from loss of the protons. So it can start to fragment, loss of hydrogen radicals actually. It can start to fragment, and we'll start to see other ions reach the detector that have actually lost hydrogen radicals. You do see a little peak here at 16, right? It's very small, but that actually is from the fact that this carbon might be carbon 13. Remember that the natural abundance of carbon 13 is about 1% of carbon atoms. So the possibility that carbon was a carbon 13 is about 1%. So that's why we see this very small peak, right? Because in carbon 13, there's an extra neutron, which is another mass unit. So it's actually one more than the molecular ion if it was carbon 12. Okay, so you saw those other signals like at 15, 14, 13, etc. Those are from loss, again, of these hydrogen radicals, forming carbocations that contain less and less hydrogens. And those will also reach the detector because they're charged, and you'll see peaks for those as well. Let's look at the mass spectrum of benzene. So if you do a calculation for benzene, you would take 6 times 12, because there's 6 carbons, plus 6 times 1, because there's 6 hydrogens. So that's going to total 78. And we actually see the molecular ion, our parent ion, which is also the base peak, right? Which is base peak means tallest peak, in the mass spectrum is at 78. So the most common fragment or piece, most common ion to reach the detector is the molecular ion, and this is ideal, right? It does do a little bit of fragmenting. You can see some of these other peaks at a lower M over Z value, but not a lot. Primarily it reaches the detector, and that's because benzene is pretty stable. So we're going to learn later that aromatic compounds have an unusual and very strong stability associated with them. So it's just less likely to fragment because the structure is pretty stable. You see that the M+1 peak here at 79 is a little bit taller than it was with methane. And that's just because with 6 carbons, you have a greater probability that at least one of those carbons will be carbon 13. And so that just increases the propensity of getting that M+1 peak. For a lot of compounds, if you're using the EI method of ionization, so the electron impact method, the molecular ion peak is not the base peak. And that's because those compounds fragment more easily. So particularly if you're using acyclic compounds, those are usually a little less stable. So acyclic compounds, and if they have a lot of functional groups and you're using electron impact, you might not even see the molecular ion at all because they fragment so readily that essentially 100% of them would fragment before the molecular ion could even reach the detector. And in that case, you would not see the molecular ion, which is not ideal because we want to confirm that we have pentane. So the easiest thing to do is look for the molecular ion. A calculation for pentane would be 5 times 12, which is 60, plus 12 hydrogens. So that would be at 72. So we do see the molecular ion, but it's definitely not the base peak. The base peak is over here at 44. So it's clearly a fragment instead of the entire molecule intact. And you do see an M+1 peak there as well at 73. Okay, so it's talking about that M+1 peak, right? It is there from carbon 13 in the sample. About 1% of carbons are carbon 13, so usually the peak is pretty small. But the more carbons, like for example for decane, when you see the molecular ion for decane, the M+1 peak is much higher, because now with 10 carbons, the likelihood that at least one of the carbons in the molecule is carbon 13 is 10-fold more probable than with methane. Okay, let's talk about the halogens, because they're actually pretty interesting. One of the things that's interesting about chlorine is that it has 2 abundant isotopes. So with most molecules, there's only 1 abundant isotope. Like for hydrogen, it's just the hydrogen atom with only 1 proton in its nucleus. For carbon, it's carbon 12, but there's 1% of carbon 13, but still overwhelmingly carbon 12 is the most abundant isotope with carbon. But with halogens, particularly chlorine and bromine, it's a different story. So with chlorine, we have 2 abundant isotopes, chlorine 35 and chlorine 37. And their abundance in nature is about a 3-to-1 ratio, or 76 to 24%. And so what we'll see is if you have a molecule that contains a chlorine, then there's 3 out of 4 chances it's chlorine 35, but there's still 1 out of 4 chances that it's chlorine 37. So that's going to give you essentially 2 different molecular ions. One when we add 35 for the mass of chlorine, and one when we add 37 for the mass of chlorine. So that looks like a molecular ion plus a molecular ion plus 2 peak. So oftentimes you'll see this sort of dual molecular ion peaks, right, in a 3-to-1 ratio when you have chlorine. So when you see something like that, it's pretty indicative that you might have a chlorine in the molecule. What about bromine? Bromine actually has nearly a 1-to-1 ratio of 2 different very abundant isotopes, bromine 79 and bromine 81. And because of that, you're going to see a very strong M+2 peak, right? So you see nearly 1-to-1 for the M and the M+2 peak. And that's because these isotopes are nearly equally abundant in nature. And each one has its own M+1 peak. So really you can think of this as 2 molecular ions with 2 M+1 peaks, or in molecular ion and M+1, a very abundant M+2 and an M+3. So the book talks about, if you're reading the chapter on mass spectrometry, they talk a lot about fragmentation patterns. So where can molecules commonly fragment? What sort of things are easily lost from a molecule? And what functional groups can you see sort of some common fragments? We're not going to do a fragment analysis. There's a reason for that. This is more of an advanced organic chemistry class where you might do a lot of pathways for fragmentation. But also now we have more gentle methods of ionization, which allow the molecules to, as a molecular ion, to reach the detector without fragmenting. And so we don't really need to do an analysis of fragments, which actually makes the analysis of a mass spectrum much easier. Okay, so one thing to mention is that there is something called high resolution mass spectrometry. And that's actually a very useful type of spectrometer to have, where you can actually, it will actually measure the mass to charge ratio, which is just relative to the mass. Since the charge on most ions is just +1, we'll actually measure it up to 4 decimal places. And this is useful for determining what is the exact formula associated with that mass. Because a lot of times we can say, okay, for sure the molecular ion is 219, but 219 might correspond to several different potential molecular formulas. So doing high resolution mass spectrometry allows us to determine which more certainty of the molecule that we're dealing with, because we can narrow it down between more than one potential molecular formula that matches a certain mass. And the reason why being able to measure up to 4 decimal places is important is actually because when you measure the atomic mass unit for a proton or a neutron to 0 decimal places, it's just 1, right? But when you look further, we see that there is actually a difference in the mass of a proton and the mass of a neutron. It's a very slight difference, but it's enough to make a difference in different molecular formulas that have a lot of protons and neutrons being added up. Because the atomic mass unit is based on carbon-12, then the value for carbon is 12.0000. But for all other atoms, there will be some numbers after the decimal place. So for example, let's say we were taking a mass spec of an unknown. With a low resolution mass spec, we might see that the molecular ion is 84. But 84 might correspond to C5H8O or C6H12. And we wouldn't really know which one it is. But if we had a high resolution mass spec, we would know to 4 decimal places. We would actually be able to distinguish the 2 masses, and we would know whether or not we had C5H8O or C6H12. Okay, so a mass spec by itself is really only suited for obtaining mass data from pure substances, because if you have a mixture, you're going to get multiple molecular ions, which might really convolute the mass spectrum. So if, for example, you need to analyze a mixture, you would want to use a different instrument that has a mass spec, but also first the sample goes through, for example, a gas chromatograph. So a lot of times you might hear about GC-MS, a GCMS, which basically has a gas chromatograph before the mass spec in terms of the sample. So the sample initially gets injected into the GC, and notice the word chromatograph, which is short for chromatography, right? So this is a way of separating compounds, just like a TLC plate separates compounds. A gas chromatograph also separates compounds based on their affinity for a mobile or a stationary phase. The mobile phase being a gas in this case, hence the term gas chromatography. And the stationary phase is usually a solid. So it goes through a long column, and compounds get separated based on affinity for that stationary phase. And then once they're separated, right, the first one would go through the mass spec by itself, right? And the next compound to get eluted from the gas column, the gas chromatography column, would then move on to the mass spec by itself. So essentially we're separating the compounds and each one goes into the mass spectrum by itself, and we can select those particular peaks and figure out the mass of all the different components of all the different compounds in our mixture, right? So we need some way to separate it before each sample is put into the mass spec, and a good way to do that is through a GC. Okay, so here's an example of what you might get for a spectrum from the GC. So the GC will separate all of the compounds, and you can see that when the compounds are getting eluted from the GC, we see a peak, basically. So in this particular mixture, there's 5 compounds, right? Because we see 5 of these peaks, and they are fairly effectively separated on the column, which is great. So one at a time, in order of earliest eluting to latest eluting, they'll be injected into the mass spec, and we'll be able to get mass data, ideally the mass of the molecular ion for each one of these. So we can get some idea of what's in our mixture based on what the mass of the compounds are in the mixture, which is really useful for things that are never going to be pure, such as blood or urine. Okay, just checking my time. All right, so to be analyzed by electron impact, generally the samples have to be of a low molecular mass or molecular weight. Okay, so basically they have to be able to be volatilized with heat, right? So they have to have a fairly low boiling point in order for them to be vaporized effectively, in order to get into the gas phase to then be bombarded by the electron stream. So that doesn't really work for really large molecules, really large biomolecules or polymers, proteins, things like that. Those are just too massive. Their boiling point is just too high to effectively get them into the gas phase before they would decompose. So that's when they started generating other ways to ionize compounds besides bombarding them with a high energy beam of electrons. So another option is the electrospray ionization, which we term ESI. And in that process, a high voltage needle actually sprays a liquid solution of the analyte into a vacuum. And the high voltage needle actually causes the molecule to be ionized. And in this case, it doesn't actually need to be in the gas phase. So it doesn't actually have to be heated, doesn't risk decomposing. So it's a much softer ionization technique because it isn't heated quite to the same extent as with EI. And the molecules then have less energy, and so they're less likely to fragment. Okay, moving on from mass spectrometry, we're going to talk a little bit about something called the degrees of unsaturation, or the hydrogen deficiency index. So one thing is for alkanes or saturated hydrocarbons like pentane or hexane, the formula for those compounds is C to the N, H to the 2N plus 2, where N is the number of carbons, basically, and the number of hydrogens. So for example, for pentane, right, we would have C5, and the number of hydrogens would then be 2 times 5 plus 2, or 12. So for any alkane, that's not a ring, okay, it can't be a cyclic alkane, just an acyclic alkane. It will match this formula, right? There will always be 2 more than twice the number of hydrogens compared to the number of carbons. But as there's an introduction of pi bonds, we actually lose hydrogens. So notice going from pentane, which is an alkane, and its molecular formula is C5H12, if one of those carbon-carbon bonds is a double bond, now the formula is C5H10. So we've actually lost 2 hydrogens. And if that is instead a triple bond, then it's C5H8. So we've actually lost 4 hydrogens than what would be, than what carbon would be able to have if it was completely saturated. So basically we say when there's a double bond present or a pi bond present, the compound is not saturated. So we say it's unsaturated. Whereas alkanes are saturated, meaning there's the maximum number of hydrogens attached to carbon that there possibly can be, right? If there's less than that, then it's unsaturated. So compounds that have a pi bond are unsaturated. Interestingly, if the compound is a cyclic compound, it is also not going to have the maximum number of hydrogens per carbon. And it will be similar to having a pi bond. And we're going to see that. And that's because you lose 2 hydrogens by bonding the terminal carbons together in a ring. So let's consider some isomers of C4H6, right? So we can see all of these structures would actually match that formula, C4H6. They either have 2 double bonds, 1 triple bond, 2 rings, or 1 ring and 1 double bond, right? So we can start to get the idea that when you have 1 unit of unsaturation, that is shown in a structure as either a ring or a pi bond. So if you look at a couple of compounds like chloroethane versus ethane, then we're actually going to see that the HDI is the same. Basically, the halogen can take the place of a hydrogen and it doesn't change anything. There's no pi bond introduced, there's no ring. So it's not going to affect the HDI calculation. Oxygens also don't affect the HDI. Nitrogens do though, because when you have a nitrogen, you have 1 more hydrogen in the molecule than would normally be expected. So that kind of generates this equation, right, which you can say that hydrogen deficiency index equals 1/2, 2 times the number of carbon plus 2, plus the number of nitrogen, minus the number of hydrogens and halogens. When you do this, apply this formula to any compound with any molecular formula, you are always going to get a value of 0 or a positive integer. So the solution to the equation must always be 0, 1, 2, 3, 4, 5, etc. It cannot be a fraction and it cannot be a negative number. If you get that, then you did something wrong with the calculation. So calculating the HDI can actually be very useful if you're just given a molecular formula and you don't know what the compound is and you're trying to figure out what the compound is. Because if, for example, you get an HDI of 0, you know the molecule cannot have any rings or any pi bonds. So that's really helpful information. That means it can't have a ketone, an aldehyde, an ester, a lot of the different functional groups that have a carbonyl, that's 1 pi bond. So it's not possible if the HDI is 0. If you have an HDI of 1, then it starts to become possible because now you have 1 pi bond or 1 ring. When you have an HDI of 2, now you have more possibilities. It could be 2 pi bonds, which could be 2 different alkenes or 1 triple bond. Or you can have 2 rings or 1 pi bond and 1 ring. So the possibilities as the HDI goes up actually become more broad. And then one other thing to note is that if you have an HDI of 4 or more, you might have an aromatic ring in your compound. Because think about the benzene ring. There's 1 ring and 3 pi bonds. So that would equal an HDI of 4.